Alright, so we're going to work on the elusive number 10, the super secret, special, tricky, hard, or difficult, usable, or status. So let's start with a diagram for this. And in this, we have velocity, we have time, we have Hannah that runs in the positive direction with a constant acceleration, and then continues on with constant speed. And what's given in the problem are these two values, that velocity is 14.7 meters per second, and it takes 6 seconds to get there. As far as knowns and unknowns go, I know that Hannah starts from rest. I know that Hannah gets to a final velocity of 14.7 meters per second over a 6-second interval. I don't know what Hannah's acceleration is over those first 6 seconds. I also don't know what Hannah's displacement is over those first 6 seconds. Looking forward to the next leg of the race, I know that her velocity is now constant for the second leg of the race, the 6 seconds plus. So that velocity is going to be 14.7 seconds. I'm sorry, meters per second. I know that the total distance covered is going to be 100 meters. And that means that the total displacement covered in the 6 plus seconds is the 100 meters of the race minus the delta x of the 6 seconds. So the distance she has to cover after the first 6 seconds, this distance is equal to the total distance minus the distance she's already covered in the first 6 seconds. And then my final question is, how long does it take her to do all of this? So the first thing that I need to know is what her displacement over the first 6 seconds is, because that is what's going to inform her displacement over the last leg of the race. So to do that, I'm thinking I'd like to use this equation right here. Delta x equals 1/2 at squared plus v initial t. The problem with this is that I don't know what the acceleration is yet. So I'm going to have to use a second equation. Let's say acceleration is delta v over t in order to find out what that acceleration is so that I can use the first equation. So I know that my change in velocity is 14.7 meters per second, and that it took her 6 seconds to achieve that, which means her acceleration was 2.45 meters per second squared during the first 6 seconds. Now that I know that, I can start plugging some numbers into my displacement equation. So delta x equals 1/2 times 2.45 meters per second squared times t squared, 6 seconds squared, plus v initial t, where v initial was 0, so that's just canceling out on that next term. So solving this out, I get 2.45 times 36 divided by 2, and that means that she covers, in the first 6 seconds, she covers a total of 44.1 meters, which is preposterous, but, you know, she's really fast. So now that I know that, I can come back over and solve the second half of this problem using my final equations over here. So delta x over the final the final leg of the race, the 6 plus seconds, is equal to the total distance of the race, 100 meters, minus the distance that she covers in the first 6 seconds, 44.1 meters. And so in the last leg of the race, she has to cover a total of 55.9 meters. Ultimately, my question is, how long does it take her to do all of this? So now I need to find a way to solve for time. Well, in the second leg, I know that her average velocity is equal to her displacement over time, and that her average velocity was 14.7 meters per second, because now she's traveling at a constant speed. I also now know how far she has to go in this leg. So now I can plug in here delta x of 55.9 meters divided by t seconds equals 14.7 meters per second. Solving for t, I get that that should take her an additional 3.8 seconds. So that's the time it takes to finish the second leg of the race. So now, last step here is to say that the total time elapsed is going to be 6 seconds from the beginning of the race plus 3.8 seconds for the next leg of the race, which will equal 9.8 total seconds to finish a 100-meter race. And there you go.